Imagine you're rowing a boat across a calm lake. You row with steady strokes, but then you decide to double your effort. Suddenly you're moving twice as fast, but still in the same direction. This is what scalar multiplication is all about. It's a way to stretch or shrink vectors by multiplying them with a single number called a scalar. Unlike vector addition or subtraction, which changes both the magnitude and direction, scalar multiplication only affects the magnitude. Think of it as adjusting the volume of the vector while keeping it pointed the same way. Let's break this down step by step, making it as simple as possible. Concept of scalar multiplication. Scalar multiplication is straightforward. 1. Multiply each component of the vector by the scalar. The vector's direction stays the same, but its magnitude changes. You can think of it like stretching a rubber band. Pull it, and it gets longer, but it still points the same way. Let's explore this with examples. Example 1. Doubling your effort, simple. You're paddling your kayak at 3 miles per hour east, but you decide to double your effort. What's your new velocity? Step 1. Represent the vector. Your initial velocity is a equals 3, 0. Step 2. Multiply by the scalar. The scalar here is 2 because you're doubling your effort. Multiply each component of a equals a by 2. 2 times a equals 2 times 3, 2 times 0, which equals 6, 0. Step 3. Interpret the result. The new vector a equals 6, 0 means you're now traveling 6 miles per hour east, twice as fast as before. Why it's helpful. Scalar multiplication makes it easy to calculate what happens when you scale up or down, like increasing effort or changing speed. Example 2. Slowing down. Intermediate. Now let's imagine you're hiking up a hill. You start walking at 4 miles per hour uphill, north. But the slope gets steeper, and you slow down to half your speed. What's your new velocity? Step 1. Represent the vector. Your initial velocity is a equals 0, 4. Step 2. Multiply by the scalar. The scalar here is 1/2 because you're reducing your speed to half. Multiply each component of a by 1/2. 1/2 times a equals 1/2 times 0, 1/2 times 4, which equals 0, 2. Step 3. Interpret the results. The new vector equals 0, 2. Means you're now traveling 2 miles per hour uphill, half your original speed. Why it's helpful? Scalar multiplication helps us model how external factors like terrain or effort affect motion without changing direction. Example 3. Scaling in 2 dimensions, advanced. Now imagine you're flying a drone. Its velocity is a combination of movements. 3 meters per second east and 4 meters per second north. You decide to increase its speed by 1.5 times. What's the drone's new velocity? Step 1. Represent the vector. The drone's initial velocity is a equals 3, 4. Step 2. Multiply by the scalar. The scalar here is 1.5. Multiply each component of a equals a by 1.5. 1.5 times a equals 1.5 times 3, 1.5 times 4, which equals 4.56. Step 3. Interpret the results. The new vector r equals 4.56 means the drone is now traveling 4.5 meters per second east and 6 meters per second north. Step 4. Find the new magnitude. To calculate the drone's new speed, the orange vector, we use the Pythagorean theorem. The magnitude of r equals the square root of 4.5 squared plus 6 squared. This equation directly applies the Pythagorean theorem to find the hypotenuse, resultant velocity. We square the horizontal component 4.5 meters per second and the vertical component 6 meters per second and add them together. The magnitude of r equals the square root of 20.25 plus 36, which equals the square root of 56.25. The magnitude of r equals 7.5 meters per second. The drone's new speed is approximately 7.5 meters per second in the same direction as before. Key takeaways from scalar multiplication. Scaling magnitude. Multiply a vector by a scalar to increase or decrease its size while keeping its direction the same. Positive versus negative scalars. Positive scalars scale the vector up. Negative scalars reverse its direction. Example, flipping a car's velocity to reverse. Practical applications. Scalar multiplication models real-world changes like increasing effort, reducing speed, or altering force without changing direction. Next steps. Now that you've mastered scaling vectors, let's explore how vectors work together in dot products and cross products, unlocking even more powerful tools for understanding motion and forces. Ready? Let's go! Dot products. Finding alignment between vectors. Imagine you're pushing a heavy box across the floor. You're pushing at an angle, trying to move it forward, but not all your effort actually moves the box. Some of it presses the box downward, making it harder to slide. How do we figure out how much of your push is actually useful? That's where the dot product comes in. It measures the part of one vector that aligns with another. Concept of the dot product. The dot product, also known as the scalar product, finds how much two vectors work together. It gives you a single number, a scalar that tells you whether the vectors are aligned, perpendicular, or working against each other. To find the angle between two vectors, here's the formula for the dot product. A dot B equals the magnitude of A times the magnitude of B times the cosine of theta, where the magnitude of A and the magnitude of B are the magnitudes of the vectors, and theta is the angle between them. The closer the angle is to 0 degrees, the more the vectors align. If the angle is 90 degrees, the dot product is 0. They're perpendicular. When to use the dot product. Measuring alignment. It tells you how much one vector contributes to another's direction. Applications in work. Physics uses the dot product to calculate work done when a force moves an object. Determining perpendicularity. If the dot product equals 0, the vectors are perpendicular. Let's break this down with examples. Example 1. Pushing a box. Simple. You're pushing a box with a force of 10N at a 30-degree angle to the floor. How much of that force actually moves the box forward? Step 1. Represent the vectors. Your push. The magnitude of A equals 10 newtons. The forward direction, the magnitude of B equals 1. We're measuring along this direction. The angle between your push and the floor is theta equals 30 degrees. Step 2. Apply the dot product formula. A dot B equals the magnitude of A times the magnitude of B times the cosine of theta. Substitute the values. A dot B equals 10 times 1 times the cosine of 30 degrees. Step 3. Solve for the result. A dot B equals 10 times 0.866, which equals 8.66 newtons. 4. Interpret the result. Only 8.66 N of your push moves the box forward. The rest of your effort presses it into the ground. Why it's helpful. The dot product shows how effective your force is in the direction you want to move. This is critical in physics when calculating work or optimizing motion. Example 2. Work done by a force, intermediate. Now imagine you're dragging a sled with a rope at a 45-degree angle to the ground. You're pulling with 50 N of force and the sled moves 10 meters forward. How much work do you do on the sled? Step 1. Represent the vectors. Your force, A equals 50 newtons. The displacement, B equals 10 meters. The angle between the force and the displacement is theta equals 45 degrees. Step 2. Apply the dot product formula. Work is calculated as work equals A dot B, which equals the magnitude of A times the magnitude of B times the cosine of theta. Substitute the values. Work equals 50 times 10 times the cosine of 45 degrees. Step 3. Solve for the result. Work equals 50 times 10 times 0.707, which equals 353.5 joules. Step 4. Interpret the result. You did 353.5 joules of work pulling the sled forward. Why it's helpful. The dot product is the foundation for understanding work in physics. It tells you how much of your force contributes to moving an object, ignoring effort wasted in other directions. Example 3. Checking perpendicularity. Advanced. You're analyzing two forces acting on a point. Force 1, A equals 3, 4. Force 2, B equals -4, 3. Are these forces perpendicular? Step 1. Use the dot product formula. For vectors in component form, A dot B equals AX times BX plus AY times BY. Here, AX and BX are the horizontal X components, while AY and BY are the vertical Y components. Here, AX is equals to 3, as we can see from the graph, while AY is 4. Similarly, BX is equals to -4, while BY is 3. Step 2. Plug in the components. A dot B equals 3 times -4 plus 4 times 3. Step 3. Solve for the result. A dot B equals 3 times -4 plus 4 times 3. Step 4. Interpret the results. Since the dot product equals 0, the vectors are perpendicular. Why it's helpful. Checking perpendicularity is essential in physics and engineering, especially for calculating torques, forces, or understanding geometry. Key takeaways from the dot product. Measures alignment. A positive dot product means vectors align, 0 means they're perpendicular, and negative means they oppose each other. Calculates work. The dot product is used to find how much force contributes to motion. Practical applications. From pushing boxes to designing machines, the dot product simplifies real-world problems. Next steps. Now that you've mastered alignment with the dot product, let's move on to the cross product, where vectors twist and spin to create new dimensions of motion. Ready to dive in? Let's go!